Okay, let's have a look at this idea of pressure. So you can exert pressure on something by actually exerting a force on it, and part of the reason that people mix up pressure and force is because they're obviously linked. So the actual size of the pressure is actually proportional to the size of the force you apply, and so people sort of think of it as a push and also force to push. So what's the big difference between them? When you look at these books that are on the table here, they all have the same mass, and so they've also got the same weight in each case. So in terms of force, the force matches as they go down on the table. But the amount of pressure they exert on the table does differ, and that's because that area of contact that's actually present there, this area of contact here, is actually different for each one. So where there's a fairly large area of contact in the first book, that one there, you'll actually get less pressure. Where the area of contact gets a bit smaller in the second book, you're getting even more pressure, and when you've got it on that corner there, resting on that edge, you're going to get the most pressure, because pressure is proportional to force, but it's also inversely proportional to the area. So if you look at that, then the amount of area that's present does change the pressure. So if you were to halve the area of contact, you will get double that pressure. Okay, if you do a tenth of the area of contact there, you'll actually get 10 times the pressure. So pressure is pretty important in that regard. You can also see that in this diagram down here. These here, you've actually got the same weight here being exerted on this block of wood, the same weight being exerted on this block of wood, because the two weights are the same. But you'll get more pressure on this second one because it's being exerted over a block of wood that's smaller. The block of wood that's smaller is pushing down on the tabletop there. You'll get more pressure there, higher pressure. So it is force, but it's also area of contact there. So just bear that in mind. Now this would also apply to just someone pushing you in the back. If they use the palm of their hand, you'll get a fairly large area, so the pressure you feel will be smaller. But if they then start poking you with your finger, like this, then you'll actually get a smaller area of contact, so again you'll get a higher pressure. And if you go even smaller area, like they would poke you with a needle like a doctor does, that pressure will be much bigger because of the much smaller area, and therefore you'll get enough to actually break through the skin, and that's how it gets in there. Other things to think about are the actual elephant here. Some animals have got a fairly big weight to them, so a large force. To reduce that overall sort of pressure there, they would have area of feet that are fairly large. So a large area of contact here will actually reduce the size of that pressure, so it will come down. Other things you can do here would be to consider people on one leg versus two legs. If they're actually on one leg, they've only got half the area of contact, so again that should double the pressure there. Now there is actually a formula you can use for pressure here. Bring that one in over here, hide those a bit. The amount of pressure you actually get will be based on the force that's acting and the area of contact, as I said before. So in this case here you've got a book that's resting on the table like we said before. It's got a weight of 100 newtons there. And it's actually got an area of contact of 0.1 square metres, so you get about 1,000 pascals. Now a pascal is actually a newton per square metre, and that should make sense because force is in newtons and area is in square metres, so logically the units will be newtons per square metre. If you actually rest the book so it's in this position here and the area of contact becomes say a tenth, that's a bit exaggerated here, you'll get 0.01 square metres, which means that you'll get a pressure that's actually 10 times greater because the area was 10 times smaller. So as that's gone down and been made 10 times smaller, we expect the pressure to become 10 times greater. Now some other things to think about with pressure is that you can actually cut much better with a sharp knife than a dull knife, because the sharpened knife actually has a much smaller area of contact, and as that area of contact goes down you will get a much greater pressure, and it's that greater pressure that actually obviously cuts through the skin of the object, or in this case through the rope and so on. That's the reason you also round off desks and stuff. Rather than having a very sharp cornered desk which has got a very small area of contact, you're much better off actually having a rounded desk which will give you a bigger area of contact and reduce that pressure on you. So that's pretty important. Here you've got someone who's actually lying on a bed of nails. Now that's going to be worse than actually lying just on a flat board, because the area of contact is going to be reduced quite a bit. But in this case it's not enough to break the skin, because they've got so many nails here that are so close together. You've still got quite a good area of overall contact on the body, and so the pressure there is not enough to break through the skin. It will certainly poke the skin and leave a mark there for a little while, probably for 10-20 minutes, but it will not break the skin there. Other applications. Some other applications that might be useful in considering pressure is if you were in a car that was stuck in the sand here, and you considered the actual tyres there, they're actually exerting a certain amount of pressure on the ground or in the sand. It's pretty high. So one of the ways of actually reducing that would be to actually increase the actual area of the contact with the tyres and the ground. So the best way of doing that would be to let some air out of the tyres. That will flatten that out, increase this lower area here, and reduce the pressure. And if you do that on all four tyres, it might actually be able to get you out of a bog situation. Another way of looking at the reverse order here is that when you're trying to actually stand on ice with a shoe, the amount of pressure you exert, even though it's slippery, is not enough to actually sort of break through the ice, but it's also not enough to sort of skate on it very well. If you want to skate properly, what you do is you actually reduce the area of contact here by wearing the skate blades. And the skate blades actually have got such a high pressure on there, the edges here will actually turn the ice and melt it and produce a layer of water that the actual ice skaters skate on. So it's really a layer of water they're actually skating on rather than a layer of ice. So that's because the high pressure formed.